For generations, scientists operated under the assumption that the cosmos, while immense, could ultimately be measured and mapped. Roughly 14 billion light-years extending in all directions, housing several hundred billion galaxies dispersed throughout the void. This picture seemed enormous, yet comprehensible. Then, the James Webb Space Telescope directed its mirrors toward regions that appeared to be absolute void, and that confidence shattered. Webb uncovered an observable cosmos stretching nearly 93 billion light-years from edge to edge, teeming with stellar systems lurking in places where nothing was anticipated to exist. It discovered fully developed galaxies existing merely 300 million years following the Big Bang, black holes expanding more rapidly than physical laws suggested possible, and formations far too enormous for their cosmic age. But the most disturbing discovery isn't the extent of Webb's vision. It's what these findings suggest about what exists past our cosmic boundary, and why the majority of reality might be permanently inaccessible. If you're prepared, tap that like button, subscribe, and let's explore together what James Webb has uncovered this time. To grasp what the James Webb Space Telescope is genuinely revealing, we must first reject the notion that space is merely something we gaze across. Within the cosmos, separation and duration are intertwined. Light propagates at an unchanging velocity, approximately 186,000 miles per second. It represents the swiftest phenomenon in existence, rapid enough to encircle our planet more than 7 times within a single second. Nevertheless, even at that remarkable speed, separation instantly transforms into postponement. The greater the distance light traverses, the more ancient the image it carries upon finally arriving. When you observe something a mile distant, you witness it as it appeared a few millionths of a second previously. When you gaze at the moon, you perceive it 8 seconds in history. When you view the sun, you aren't seeing it as it currently exists, but as it appeared 8 minutes earlier. The heavens aren't a real-time display of reality. They're a stream of information arriving delayed. These postponements are so minuscule that we never register them in everyday existence. Our minds process the world as instantaneous and uninterrupted. But as our observation extends outward, the delays expand, and ultimately, they reshape how the cosmos itself must be comprehended. The closest star past our sun appears to us as it existed more than 4 years previously. The heart of the Milky Way is witnessed as it existed 26,000 years in history. And when we peer beyond our galaxy into the immense spaces separating stars, we're no longer witnessing the universe as it exists presently. We're reading earlier chapters of a narrative already billions of years ancient. The nocturnal sky then isn't a snapshot, it's an archive. Every point of luminosity carries a timestamp. Every photon serves as a messenger from a different moment in cosmic chronicle. The more distant its origin, the more ancient the message it delivers. The difficulty is that the cosmos doesn't preserve these messages unchanged. As reality expands, space itself elongates. And when space elongates, it elongates the light traveling through it. Wavelengths grow extended. Energetic blue and ultraviolet light transitions toward red and slips into infrared. This effect, recognized as redshift, isn't merely a visual alteration. It's a record of how extensively the universe has expanded since the light commenced its journey. Redshift functions like a cosmic timepiece. The more elongated the light, the longer it has been traveling, and the earlier in the universe's chronicle it was released. For generations, astronomers depended on telescopes optimized for visible and ultraviolet light. The limited slice of the spectrum human vision evolved to perceive. Instruments like Hubble transformed our comprehension of neighboring galaxies, star-forming territories, and the large-scale structure of reality. But as scientists attempted to look further back in duration, the universe started to fade. Not because it wasn't present, because its light had transformed. Ancient galaxies didn't vanish. Their light simply drifted past the range those telescopes could capture. The James Webb Space Telescope was constructed to pursue that missing light. Its mirror extends more than 21 feet and is layered with a microscopically thin coating of gold. Selected because gold reflects infrared light with extraordinary effectiveness. Webb doesn't orbit our planet. It functions nearly 1 million miles distant at a stable gravitational location where it can remain directed steadily, protected from heat and brightness. That separation permits Webb to maintain extremely cold temperatures, and that coldness is crucial. Infrared light is intimately connected to thermal energy, and a warm telescope would overwhelm the faint signals it's attempting to capture. Webb had to become silent enough to hear the cosmos whisper. When Webb stares into a territory of sky that appears completely black to our vision, it isn't searching for emptiness. It's waiting for photons that have been elongated almost to invisibility by billions of years of cosmic expansion. Those photons arrive gradually, sometimes individually. Webb may stare at the identical patch of sky for numerous hours, even days, patiently gathering light that has crossed nearly the entire observable cosmos. And what it discovers there isn't a quiet, tentative universe just beginning to take shape. It discovers a cosmos that is already bustling. Some of the galaxies Webb has identified formed when reality was only approximately 300 million years ancient, less than 3% of its current age. To comprehend how early that is, imagine compressing the entire chronicle of the cosmos into a single year. These galaxies would manifest on January the 2nd. According to long-established models, this era, frequently called cosmic dawn, should have been relatively dim. The first stars were anticipated to ignite gradually. Early galaxies were predicted to be small, delicate collections of gas and stars, requiring hundreds of millions of years to develop into anything substantial. But Webb witnessed galaxies that were already brilliant, already massive, and already forming stars at intense rates. Now, some were luminous enough that even if they were much more distant, Webb could still capture them. That brilliance matters. Brilliant galaxies require large populations of stars, and stars do more than shine. Inside their cores, they forge heavier elements like carbon and oxygen, elements that didn't exist in the universe's earliest moments. Those elements are released only when stars perish. When Webb detects heavy elements in such young galaxies, it's witnessing evidence that earlier generations of stars must have already formed, existed, and concluded their lives. The cosmos had already gone through multiple cycles of creation and destruction far sooner than anticipated. The cosmic timepiece was being pushed backward. The universe didn't slowly ease into complexity. It accelerated toward it. There's also something quietly humbling about the act of witnessing this ancient light. Webb doesn't capture these images instantly. It gathers photons that have been traveling for more than 13 billion years. Photons that commenced their journey when the universe was young and unfamiliar. When that light started moving, our planet didn't exist. The sun hadn't formed. The Milky Way was still assembling itself from clouds of gas and dark matter, oceans, life, civilizations. Every chapter of human chronicle unfolded while those photons were already on their way. By the time Webb captures them, we're not witnessing events happening presently. We're witnessing moments that happened once, long previously, preserved in transit, and never to be repeated in quite the same manner. This is why astronomers say James Webb doesn't just look far distant. It looks backward through duration. Separation becomes a timeline. Nearby objects show the universe closer to the present. Distant objects reveal earlier and earlier stages of cosmic chronicle. Yet even Webb's extraordinary vision has a fundamental boundary. No telescope, regardless of how powerful, can see beyond a boundary established by physics itself. That boundary is defined by how far light has been able to travel since the universe commenced. It's called the observable universe, a vast sphere centered on us with a radius of approximately 46.5 billion light years. Webb is now pushing observations closer to that boundary than ever before, identifying galaxies at distances once thought unreachable. But even Webb cannot see beyond the cosmic horizon. And this is where the realization becomes unsettling. Space doesn't terminate at the edge of what we can witness. Beyond that horizon, galaxies still exist. Stars still ignite and perish. Black holes still merge. Entire cosmic chronicles unfold in regions forever hidden from us. Not because technology is lacking, but because space itself is expanding too rapidly. James Webb has not only shown us how far our vision can extend, it has shown us how much of reality lies permanently beyond it. And as we absorb what Webb has revealed within our observable bubble, the early brilliance, the rapid formation of structure, the sheer abundance of galaxies, a deeper question begins to emerge. If this much exists in the small fraction of the cosmos we can witness, What does that say about the true magnitude of everything that exists beyond our view? For most of modern astronomy, the early cosmos was imagined as a quiet and delicate place. Following the Big Bang, space expanded rapidly, temperatures dropped, and matter spread out almost evenly in every direction. Tiny fluctuations existed, territories that were slightly denser than others, but gravity was anticipated to work gradually, patiently pulling matter together over vast spans of duration. In this picture, the first stars ignited reluctantly. Gas needed duration to cool. Dark matter halos needed duration to develop. Galaxies, when they finally appeared, were anticipated to be small and faint, delicate structures that would require hundreds of millions of years to mature into anything substantial. The cosmos, according to this model, learned to walk before it learned to run. That expectation shaped generations of theory. So when the James Webb Space Telescope commenced surveying the early cosmos, astronomers anticipated scarcity, a few primitive galaxies here and there, dim objects clinging to existence in a young universe still finding its footing. Instead, Webb discovered crowds. Again and again, brilliant galaxies appeared in eras that should have been nearly empty. These weren't faint sparks barely holding together. They were already busy systems producing stars at rates comparable to or exceeding those of much later galaxies. The surprise wasn't the discovery of one strange object. It was the pattern. Within the universe's first 500 million years, Webb identified galaxies emitting enormous amounts of light. Some contained hundreds of millions, even billions of stellar masses worth of material. That amount of mass should have required far more duration to assemble than the cosmos had available. Gravity is powerful, but it isn't rapid. Gas must lose energy before it can collapse. Dark matter halos must accumulate enough mass to trap ordinary matter. Stars require millions of years to form, and those stars must exist and perish to enrich their surroundings with heavier elements. Each step imposes a minimum timescale. Compress the sequence too much, and the physics stops functioning. And yet, the galaxies were already present. One of the most unsettling aspects of these discoveries was not just the magnitude or brilliance of early galaxies, but their chemical maturity. Webb's spectroscopic measurements reveal signatures of carbon, oxygen, and nitrogen, elements that don't exist in meaningful quantities immediately following the Big Bang. These elements are forged inside stars. Their presence in such young galaxies means something unavoidable. At least one earlier generation of stars must have already formed, burned through their fuel, and concluded their lives, spreading heavy elements into space. All within the universe's first few hundred million years, the cosmic timepiece was being pushed backward. To comprehend why this troubled astronomers so profoundly, it helps to think of galaxy formation like constructing a city. You cannot build skyscrapers before roads exist. You cannot pour concrete before steel is produced. Each stage depends on the one before it. The early cosmos was supposed to be laying foundations. Webb discovered finished buildings. This growing mismatch between theory and observation became recognized as the too much light too early problem. When astronomers calculated how much total light galaxies should produce during the universe's first billion years, their predictions fell short. Webb's observations exceeded those predictions by factors of 2, 5, and sometimes even 10. That kind of discrepancy isn't a rounding error. It's a signal. Scientists did what they always do when faced with something this unsettling. They questioned the measurements. They rechecked the instruments. They reanalyzed the data. They asked whether dust, gravitational lensing, or observational bias could be making galaxies appear brighter or more massive than they truly were. Again and again, the result held. The early cosmos was not dim. It was luminous. Some of these early galaxies were so massive that researchers briefly referred to them as universe breakers, objects whose existence seemed to violate the limits imposed by cosmology itself. According to standard models, galaxies of that magnitude should not exist at those ages, not unless something fundamental about early cosmic evolution was misunderstood. At first, some astronomers hoped the masses were overestimated. Perhaps the light wasn't coming from stars alone. Perhaps supermassive black holes at galactic centers were contributing additional brilliance, making galaxies appear larger than they really were. Further analysis showed that this explanation helped, but only partially. Yes, Some early galaxies do host extremely active black holes whose energy inflates their apparent brilliance. Accounting for that reduced the most extreme discrepancies. But even after those corrections, the early cosmos still contained roughly twice as many massive galaxies as theory predicted. The tension eased. It didn't disappear. This pattern repeated across multiple surveys. Webb looked in different directions at different territories of sky using different instruments and wavelengths. Each occasion, the result was identical. The early cosmos was crowded. Galaxies formed quickly. Star formation proceeded with startling effectiveness. This forced astronomers to reconsider a basic assumption: how efficiently the cosmos could transform gas into stars. In the modern cosmos, star formation is surprisingly inefficient. Most of the gas inside galaxies never becomes stars. It gets heated, stirred by turbulence, blown away by stellar winds, or disrupted by radiation. A massive molecular cloud may spend millions of years producing only a modest number of stars before dispersing. Early galaxies appear to have played by different rules. One possibility is that the early cosmos was simply denser. With matter packed more tightly together, gas clouds collided more frequently, triggering rapid collapse. Another idea is that the first stars formed from nearly pure hydrogen and helium without heavier elements to complicate cooling processes. Under the right conditions, this simpler gas may have collapsed more directly than modern metal-rich gas. Mergers likely played a role as well. In the early cosmos, galaxies were closer together. Collisions were more frequent. When galaxies merge, gas is driven toward their centers, compressed to extreme densities, and ignites intense bursts of star formation. A galaxy could build much of its mass in short, violent episodes, rather than through slow, steady growth. Each of these ideas helps explain part of the picture. None fully resolves it. At the centers of many of these early galaxies lies another mystery entirely. Webb has identified supermassive black holes already in place when the cosmos was less than 500 million years ancient. Some of them weigh millions or even billions of times the mass of our Sun. According to conventional physics, that shouldn't be possible. Black holes form when massive stars collapse. The resulting black hole may weigh tens of solar masses. From there, it can expand by consuming surrounding matter, but that growth is limited. As material falls in, it heats up and radiates energy, pushing back against further infall. Even under ideal conditions, constructing a billion solar mass black hole should require far longer than the early cosmos allowed. Yet, Webb keeps discovering them. This has forced astronomers to consider possibilities that once seemed extreme. Perhaps some black holes formed through the direct collapse of massive gas clouds, skipping the stellar stage entirely. Perhaps the first stars grew thousands of times more massive than modern stars, collapsing directly into large black holes. Perhaps black hole mergers were far more common in the dense early cosmos than we once assumed. None of these ideas has been confirmed. None can be ruled out. What makes this period so important is that these early galaxies and black holes shaped everything that followed. Their radiation transformed the cosmos, stripping electrons from hydrogen atoms during an era recognized as rayonization. Their supernovae enriched space with heavy elements. Their gravity pulled matter into the first large-scale structures. If they formed earlier and more efficiently than anticipated, then the entire timeline of cosmic evolution shifts. And as Webb continues to look deeper, the pattern becomes harder to ignore. The cosmos did not wait patiently to become complex. It rushed. It assembled stars, galaxies, and black holes at a pace that challenges our best equations, which leads to an unavoidable realization. If the cosmos could construct this much structure so quickly, then the magnitude of what exists today, after billions more years of growth, may be far larger than we ever imagined. And that realization becomes impossible to escape when Webb does something even more unsettling. It counts how many galaxies actually exist. For most of the 20th century, astronomers believed they had reached a reasonable answer to one of the biggest questions imaginable. How many galaxies exist in reality? The method was straightforward in principle, even if challenging in practice. Point a powerful telescope at a tiny, seemingly empty patch of sky. Count every galaxy you can capture, and then scale that number up to cover the entire observable cosmos. When the Hubble Space Telescope performed its deepest observations, it revealed nearly 10,000 galaxies in a territory of sky no larger than a grain of sand held at arm's length. That image was shocking at the time. From it, astronomers estimated that the cosmos contained a few hundred billion galaxies. The number was almost impossible to comprehend, and for years it stood. Then the James Webb Space Telescope looked at the identical darkness. Where Hubble witnessed black gaps between galaxies, Webb witnessed faint infrared glows. Where Hubble detected smudges barely rising above the noise, Webb resolved structure. Territories that once felt empty suddenly revealed themselves as crowded, layered, and alive with distant systems that had been invisible before. This difference was not a failure of Hubble. It was a limitation of wavelength. As the cosmos expands, the light from distant galaxies elongates into the infrared. By the time that light reaches us, it no longer lives in the visible range that Hubble was designed to study. The galaxies were always present. Their light had simply slipped past our vision. Webb was constructed to catch it. In one of its most ambitious observations, Webb surveyed a territory of sky only slightly larger than 3 full moons placed side by side. For hundreds of hours, it collected more than 10,000 individual exposures, each one capturing faint infrared signals that had traveled across cosmic duration. When those images were combined, the result was staggering. Nearly 800,000 distinct galaxies filled the frame. 800,000 galaxies in a patch of sky most people would dismiss as empty. To grasp the magnitude of that result, imagine printing the famous Hubble Ultra Deep Field on a standard sheet of paper. To show the Webb image at the identical level of detail, the print would need to be more than 13 feet tall and 13 feet wide. A wall-sized mural of cosmic chronicle. And every point of light in that mural isn't a star. It's a galaxy. Each of those galaxies contains millions, billions, or even trillions of stars. Many host planetary systems, many contain complex chemistry, dust, and heavy elements forged by generations of stars. The cosmos, it turns out, isn't sparsely populated with isolated islands of matter drifting through darkness. It's densely packed, layered with structure at every magnitude. What makes this discovery even more powerful is that Webb didn't simply count galaxies, it measured them. For each galaxy, astronomers can estimate its separation, its mass, its rate of star formation, and their approximate age. That allows scientists to reconstruct how galaxies changed over nearly the entire chronicle of the cosmos, tracking growth from early cosmic dawn to the present day. And when they did that, a deeper pattern emerged. Galaxies aren't scattered randomly through space. They cluster, they align, they trace invisible pathways. On the largest magnitudes, the cosmos resembles a vast cosmic web. Long filaments of matter, stretching tens and hundreds of millions of light years, intersecting at dense nodes where galaxy clusters form and separated by enormous voids where almost nothing exists. This structure had been predicted for generations, but Webb revealed it with unprecedented clarity. Many of the galaxies Webb identified were hidden behind dust that blocks visible light, but allows infrared wavelengths to pass through. Entire populations of dusty star-forming galaxies suddenly appeared, filling in gaps where earlier surveys witnessed emptiness. The cosmic web didn't just become clearer, it became more crowded. This matters because the distribution of galaxies isn't random decoration. It's a record of how the cosmos grew. Shortly following the Big Bang, matter was spread almost evenly throughout space, with tiny fluctuations in density imprinted during the universe's earliest moments. Territories that were slightly denser than average exerted slightly stronger gravity. Over duration, matter flowed toward those territories, amplifying the differences. Gravity carved space into filaments and nodes, draining matter from surrounding territories and leaving behind vast voids. A useful analogy is rainfall over uneven terrain. Water drains into valleys, carving rivers and channels, while higher ground is left dry. Over duration, a structured landscape emerges. The cosmos evolved in much the identical manner, except the flowing substance was matter itself. Webb's observations show that this process was already well underway, surprisingly early in cosmic chronicle. Filaments tens of millions of light years long existed when the cosmos was only a few billion years ancient. Some structures were so large and so organized that they challenged expectations about how quickly matter could arrange itself. One striking example is a structure astronomers call the cosmic vine. It's a chain of at least 20 closely packed galaxies stretching more than 13 million light-years across. These galaxies existed when the cosmos was still young. Yet the structure rivals much older formations in magnitude. What makes the cosmic vine especially intriguing isn't just its magnitude, but its state. Several of its largest galaxies have already stopped forming stars. They're quiescent, meaning they have exhausted or lost the gas needed to create new stars. This is unusual so early in cosmic chronicle, when most galaxies are still actively forming stars. The implication is that environment matters. Galaxies in dense territories evolve differently than isolated ones. Interactions, mergers, and the harsh conditions of crowded space can accelerate a galaxy's life cycle, forcing it to develop rapidly and burn out early. And this isn't an isolated case. Using Webb data, astronomers compiled the deepest and most comprehensive catalog of galaxy groups ever assembled. They identified more than 1,600 galaxy groups and protoclusters spanning from approximately 12 billion years previously to just a few billion years previously. These groups represent the building blocks of today's massive galaxy clusters. By comparing groups at different separations, scientists can watch structure formation unfold over duration. Early groups appear chaotic, with irregular galaxies forming stars at high rates. Later groups show more order. Galaxies become smoother. Star formation slows, and gravity begins to dominate over turbulence and gas inflow. This continuous view across billions of years was simply not possible before Webb. Yet for all this density and organization, the cosmos is also defined by its emptiness. Between the filaments of the cosmic web lie vast voids, territories spanning tens to hundreds of millions of light years that contain very few galaxies. These voids aren't small gaps. They're the largest contiguous structures in the cosmos by volume. If you could place yourself at the center of one of these voids and look in any direction, you would witness darkness stretching for tens of millions of light years before encountering the nearest galaxy. Entire territories of space failed to accumulate matter simply because gravity pulled that matter elsewhere. Webb's deep field images capture this contrast vividly. In the identical frame, dense clusters of galaxies appear alongside yawning black territories containing almost nothing. The cosmos is simultaneously crowded and empty, rich and sparse, structured and desolate, depending on where you look. This brings us back to the numbers. If Webb's deep fields are representative and multiple observations in different directions suggest they are, then the total number of galaxies in the observable cosmos may not be hundreds of billions, but trillions. For every galaxy we once thought existed, there may be 10 more hiding beyond what earlier telescopes could capture. That revision changes everything. More galaxies mean more stars. More stars mean more planets. More planets mean more opportunities for complexity to arise. The cosmos becomes not just larger in magnitude, but richer in possibility. Yet even this staggering abundance exists only within the observable cosmos. Beyond that boundary, space continues. Galaxies continue. Structure continues. James Webb has shown us that even the portion of reality we can witness is vastly larger and more crowded than we believed. And that realization forces an even deeper question. If reality is this rich within our visible horizon, what does that say about the magnitude of everything we can never observe? At first glance, the cosmos seems easy to measure. The Big Bang happened approximately 13.8 billion years previously. Light travels at a fixed velocity. So it feels natural to assume that the farthest objects we can witness should be approximately 13.8 billion light years distant. For a long duration, even scientists spoke about the cosmos as if that were accurate. But that intuition quietly breaks down the moment we take cosmic expansion seriously. The observable cosmos doesn't have a radius of 13.8 billion light years. It has a radius of approximately 46.5 billion light years, making its full diameter roughly 93 billion light years. This isn't speculation or artistic license. It's a measured result supported by observations of cosmic expansion and the behavior of ancient light. The reason this number feels impossible is because it clashes with how we instinctively think about motion. Nothing can travel faster than light through space. And that rule still holds. No galaxy is racing through space at impossible speeds. No signal is breaking the cosmic speed limit. Instead, The cosmos has found a method to grow far larger without violating any laws of physics. It does this by stretching space itself. When we say distant galaxies are moving away from us, it's tempting to picture them flying outward, like fragments from an explosion. That image is deeply misleading. On large magnitudes, galaxies aren't really moving through space at all. They're being carried apart as the space between them expands. A familiar analogy helps make this intuitive. Imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot moves farther away from every other dot. None of the dots are at the center. None of them are moving across the surface under their own power. The surface itself is stretching, and the dots simply go along for the ride. The cosmos behaves in much the identical manner. When a distant galaxy emitted the light we capture today, it was far closer to us than it is presently. Over billions of years, while that light was traveling toward our planet, the space between us and the galaxy expanded continuously. By the time the light finally arrived, the galaxy that emitted it had been carried tens of billions of light years farther away. This is why we can observe galaxies whose light has been traveling for 13.5 billion years, even though their current separation is more than 46 billion light years. Light isn't simply crossing a fixed separation. It's moving through a separation that is growing while it travels. In effect, light has been running on a cosmic treadmill. Early in the universe's chronicle, expansion was slower. Light made steady progress. As duration passed, expansion accelerated, stretching separations faster and faster. Some photons managed to reach us because they started their journey early enough before the expansion rate became overwhelming. Others never will. This creates a boundary recognized as the cosmic horizon. The cosmic horizon isn't a wall or an edge in space. There's no place where the cosmos suddenly stops. Instead, it's the limit of what can ever be observed from our location. Given the finite age of the cosmos and the manner space expands beyond that horizon, light simply cannot reach us. Not because it lacks duration, but because the space it must cross grows faster than light can traverse it. And this is where the cosmos becomes deeply unsettling. Space doesn't terminate at the cosmic horizon. We know this because the cosmos looks essentially identical in every direction we observe. The distribution of galaxies doesn't thin out toward an edge. The cosmic microwave background, the faint afterglow of the Big Bang, appears almost perfectly uniform across the entire sky. That smoothness would be impossible if space abruptly concluded just beyond our view. So the cosmos extends beyond what we can witness. But it does so in a manner that permanently hides much of itself. Beyond 46.5 billion light years, galaxies still exist. Stars still ignite and perish. Black holes still merge. Entire cosmic chronicles unfold in territories that will never influence us and can never be influenced by us. No signal from those territories will ever reach our planet. Not because our technology is inadequate, but because the structure of spacetime itself prevents it. Even more unsettling, this boundary isn't fixed. As duration passes, the observable cosmos grows larger, because light from more distant territories has had more duration to reach us. The horizon creeps outward, but at the identical moment, cosmic expansion is accelerating, driven by dark energy. Space itself is stretching faster presently than it did in history. These two effects compete with one another. The result is a cosmos where some objects briefly become observable, only to later slip beyond reach forever. Galaxies we can witness today aren't guaranteed to remain visible indefinitely. Their light will continue to stretch, shifting into longer and longer wavelengths. Eventually, that light becomes so diluted and redshifted that no telescope could ever capture it. From our perspective, those galaxies will appear frozen at a particular moment in their chronicle, slowly fading until they vanish completely. This isn't a theoretical curiosity. It's a direct consequence of measured expansion rates. If the cosmos continues behaving as it does presently, then in roughly 100 to 150 billion years, every galaxy outside our local gravitationally bound group will cross the cosmic horizon. Future observers would witness a cosmos containing only a small cluster of nearby galaxies surrounded by darkness. The evidence of cosmic expansion, the cosmic microwave background, and the vast web of distant galaxies would be gone. They might never know that anything else ever existed. This leads to a profound shift in perspective. The observable cosmos isn't the cosmos. It's simply the portion of reality that happens to be observable from where we stand at this moment in cosmic duration. Move to another galaxy, and the observable cosmos changes. Different galaxies enter view, others disappear beyond the horizon. Every location in space defines its own observable cosmos. This creates strange and counterintuitive situations. Two galaxies can both be observable from our planet, yet unable to observe each other. They may lie on opposite sides of our horizon. Light from both reaches us, but light from one cannot reach the other. From their perspectives, our planet itself may lie beyond their cosmic horizon. There's no privileged vantage point, no center, no location from which the entire cosmos can be witnessed. Every observer, regardless of where they are, sits at the center of their own observable bubble. This is why the James Webb Space Telescope is so transformative. By pushing observations closer to the cosmic horizon than ever before, Webb forces us to confront the limits of what observation can achieve. When Webb captures galaxies at extreme redshifts, it's not just showing us ancient objects, it's showing us the boundary of causal connection. Those galaxies are no longer where their light commenced. Their current state, their later mergers, transformations, and possible destruction is unknowable to us. That information is still traveling through space, stretched and diluted by expansion, and in many cases will never arrive. What we witness isn't what is, it's what was. And even that view is incomplete. Beyond the observable horizon lies the unobservable cosmos, territories that may contain galaxies, clusters, and structures just as rich and complex as those we witness. Some models suggest the cosmos may be infinite, others propose it's finite, but unimaginably large. Either manner, the observable cosmos is almost certainly only a small fraction of the whole. James Webb hasn't revealed the edge of reality. It has revealed that there's no accessible edge at all. And as this realization settles in, another question becomes unavoidable. If most of reality is hidden by expansion, if vast territories of existence are permanently beyond reach, then something must be driving that expansion to accelerate. To comprehend that force, we have to confront the most dominant and most mysterious ingredient of the cosmos itself. For most of the 20th century, the story of cosmic expansion seemed straightforward. The cosmos commenced in the Big Bang. Everything rushed outward, and gravity gradually worked to slow that expansion down. Astronomers debated whether the cosmos would expand forever or eventually collapse back in on itself. But the underlying assumption was identical in every scenario. Gravity was in control. That assumption didn't survive contact with observation. In the late 1990s, astronomers studying distant stellar explosions noticed something deeply unsettling. These explosions, recognized as type Ia supernovae, shine with a remarkably consistent brilliance. Because of that reliability, they act like cosmic mile markers. By comparing how brilliant a supernova appears to how brilliant it should be, scientists can calculate its separation. Combine that separation with how rapidly the host galaxy is receding, and the expansion chronicle of the cosmos reveals itself. What those measurements showed was the opposite of what anyone anticipated. The cosmos was not slowing down, it was speeding up. Distant galaxies were farther distant than they should have been if expansion were gradually easing under gravity's pull. Something was pushing space apart, not just preserving the expansion, but accelerating it. The farther back astronomers looked, the clearer the pattern became. Expansion had been gaining velocity for billions of years. To account for this behavior, cosmology was forced to introduce a new ingredient: dark energy. Dark energy isn't something we can witness, touch, or directly capture. It doesn't emit light. It doesn't absorb radiation. It doesn't clump into stars, galaxies, or clouds. Its existence is inferred entirely from its effect on the universe's expansion, and that effect is overwhelming. Measurements presently indicate that dark energy makes up roughly 68% of everything that exists. Ordinary matter, everything from galaxies and stars to planets and people, accounts for less than 5%. Dark matter makes up most of the remainder. The cosmos we can witness, the cosmos that feels solid and familiar, is a minor component of reality. What makes dark energy especially unsettling is how it behaves as the cosmos grows. Normal matter becomes diluted as space expands. double the volume of space, and the density of matter drops by half. Radiation thins out even faster. Dark energy doesn't follow these rules. Its density remains constant even as the cosmos expands. As space grows larger, the total amount of dark energy increases. This creates a runaway effect. More space means more dark energy. More dark energy drives faster expansion. Faster expansion creates more space. Over billions of years, this feedback loop has shifted the balance of power in the cosmos. Early on, matter dominated. Gravity sculpted galaxies, stars, and the cosmic web. But as the cosmos expanded and matter spread thinner, dark energy quietly took over. Approximately 5 billion years previously, it became the dominant influence on cosmic expansion. The James Webb Space Telescope doesn't capture dark energy directly, but it witnesses its fingerprints everywhere. The extreme stretching of ancient light, the immense magnitude of the observable cosmos, and the manner distant galaxies recede all reflect the influence of this invisible force. Without dark energy, the cosmos would be far smaller. The cosmic horizon would sit much closer. Vast territories we can witness today would never have been observable at all. Dark energy does more than shape the present. It determines the universe's future. If dark energy remains constant, as current observations suggest, then expansion will continue forever, accelerating as duration passes. Galaxy clusters will remain gravitationally bound, but everything outside them will gradually slip beyond the cosmic horizon. Trillions of years from presently, observers inside a galaxy like the Milky Way would witness a lonely cosmos filled with stars nearby, but empty beyond. The cosmos would still exist, but it would look almost vacant. Yet, this picture is complicated by one of the most serious unresolved problems in modern cosmology. A problem that James Webb hasn't erased, but instead made harder to ignore. When scientists measure how rapidly the cosmos is expanding today, they don't get one answer, they get two. One method looks deep into history by studying the cosmic microwave background, the faint afterglow released when the cosmos was only approximately 380,000 years ancient. From the subtle patterns in that radiation, scientists infer an expansion rate of approximately 67 kilometers per second per megaparsec. The second method looks nearby. Astronomers measure separations to galaxies using Cepheid variable stars and type Ia supernovae, then compare those separations to how rapidly the galaxies are receding. This approach consistently produces a higher value around 73 kilometers per second per megaparsec. Both measurements are precise. Both have been repeated many occasions. Both have been scrutinized for errors. They don't agree. This discrepancy is recognized as the Hubble tension, and it represents one of the deepest cracks in our comprehension of reality. James Webb was anticipated to clarify the situation by providing cleaner, more accurate separation measurements. Instead, Webb confirmed the higher expansion rate measured in the nearby cosmos. The tension didn't disappear. It sharpened. This leaves cosmology in an uncomfortable position. Either something is wrong with our measurements, something is wrong with our assumptions, or something fundamental is missing from our models of reality. One possibility is that dark energy isn't constant after all. Its strength may have changed over cosmic duration, altering the expansion rate in manners our current models don't capture. Another possibility is that unknown physics affects how light travels across enormous separations, subtly biasing measurements. Or the early cosmos itself may have behaved differently than we assume, imprinting expansion behavior that evolves in unexpected manners. Each possibility carries profound consequences. The expansion rate determines the universe's age, its magnitude, and its ultimate fate. If we're misunderstanding it, then many conclusions drawn from generations of cosmological research may need revision. The problem isn't cosmetic. It cuts to the foundation of how we describe reality. There's also a more extreme scenario that cannot yet be ruled out. If dark energy grows stronger over duration instead of remaining constant, expansion could eventually overwhelm gravity, even on smaller magnitudes. Galaxy clusters would be pulled apart. Galaxies themselves would dissolve. Star systems, planets, molecules, and eventually atoms could be torn apart in a hypothetical future recognized as the Big Rip. Current data doesn't favor this outcome, but uncertainties remain. Measuring dark energy precisely is extraordinarily difficult, and small changes in its behavior could have enormous long-term consequences. What is already clear is that dark energy dominates the cosmos. It stretches space, hides vast territories of reality beyond our reach, and determines what future observers will be able to witness. It's the reason the observable cosmos spans 93 billion light-years. It's the reason most of existence will forever remain invisible. And yet, dark energy alone doesn't explain the cosmos we observe. Because while it pulls space apart on the largest magnitudes, something else must pull matter together on smaller ones. Something must counter expansion locally, allowing galaxies to form, clusters to develop, and structure to emerge instead of dissolving into uniform fog. That force is equally invisible, equally mysterious, and absolutely essential. To comprehend how the cosmos holds itself together, even as it expands, we have to turn to the unseen framework that shapes every galaxy, every cluster, and every filament of the cosmic web. If dark energy governs how the cosmos expands, then dark matter governs how it holds itself together. Without it, the cosmos revealed by the James Webb Space Telescope wouldn't exist in any recognizable form. Galaxies would never have assembled. Clusters would have flown apart. And the vast filamentary structure, stretching across the cosmos, would have remained a nearly uniform fog of matter. Dark matter doesn't shine. It doesn't absorb light. It doesn't emit radiation of any kind we can directly capture. And yet, it outweighs everything we can witness by more than 5-1. Roughly 85% of all matter in the cosmos is dark matter, detectable only through its gravitational influence. Every star, planet, nebula, and galaxy is constructed within a framework dominated by something fundamentally invisible. The first clues to its existence emerged nearly a century previously, when astronomers noticed that galaxies were behaving in manners that made no sense. Stars in the outer territories of spiral galaxies were orbiting far too rapidly. According to the gravity generated by visible matter alone, those stars should have been flung into intergalactic space. Instead, they remained bound, moving as if each galaxy were embedded in a massive unseen halo. That unseen mass was dark matter. As observations expanded, the evidence became impossible to ignore. Entire galaxy clusters showed the identical problem on much larger magnitudes. Individual galaxies within clusters moved too quickly to be held together by stars and gas alone. Gravitational lensing revealed distortions in background galaxies far stronger than visible matter could produce. Again and again, the conclusion was unavoidable. Most of the universe's matter is invisible. What makes dark matter so important isn't just how much of it exists, but how it behaves. Unlike ordinary matter, dark matter doesn't collide with itself or lose energy by emitting radiation. It passes through space almost frictionlessly. This allowed it to commence clumping extraordinarily early in cosmic chronicle. Shortly following the Big Bang, the cosmos was nearly uniform, with tiny density fluctuations imprinted during its earliest moments. Dark matter responded to those fluctuations first. While ordinary matter remained hot and resisted collapse, dark matter quietly gathered into growing concentrations, forming massive invisible halos long before the first stars ignited. These halos became the scaffolding of reality. As the cosmos cooled, ordinary matter commenced falling into these dark matter wells. Gas collected, compressed, and eventually ignited nuclear fusion. Stars formed, galaxies assembled. Not randomly, but precisely where dark matter had already gathered. The visible cosmos traces an invisible blueprint laid down billions of years earlier. This process produced one of the most striking features of reality, the cosmic web. On the largest magnitudes, matter is arranged in vast filaments stretching tens to hundreds of millions of light years across. These filaments intersect at dense nodes where galaxy clusters form. Between them lie enormous voids, territories so empty they contain almost no galaxies at all. This structure isn't artistic coincidence. It's the natural outcome of gravity acting on dark matter over cosmic duration. James Webb's observations have brought this architecture into sharper focus than ever before. By cataloging hundreds of thousands of galaxies and measuring their separations, astronomers can map the three-dimensional distribution of matter across the cosmos. The pattern is unmistakable. Galaxies line up along filaments. They cluster at intersections. They avoid vast, empty territories. The visible cosmos follows an invisible skeleton. What makes Webb especially powerful is its ability to witness through dust and capture faint, distant galaxies that previous surveys missed. This fills in gaps in the cosmic web, revealing how early these structures emerged. Webb has shown that filaments were already well established when the cosmos was only a few billion years ancient, and that matter was flowing along them into growing clusters. This flow isn't just a metaphor. Simulations and observations indicate that gas streams along dark matter filaments like traffic along cosmic highways. Galaxies develop not only by forming stars internally, but by continuously accreting fresh material delivered along these invisible routes. Even our own galaxy participates in this process. The Milky Way resides on a filament connecting larger structures, drifting through space along pathways defined by dark matter. On these magnitudes, motion is guided, not random. For generations, the role of dark matter in shaping the cosmic web rested largely on simulations and indirect evidence. But recently, astronomers achieved something remarkable. They captured dark matter directly along the filaments themselves. Using gravitational lensing, scientists measured how light from distant background galaxies was subtly distorted as it passed through territories where filaments were predicted to exist. The distortions were faint and difficult to capture, but consistent. They revealed mass where no visible matter could account for it. Dark matter was not just concentrated in clusters, it was stretched across space, threading the cosmos together. This transformed the cosmic web from a theoretical construct into an observed structure. The cosmos isn't a loose collection of galaxies drifting apart. It's an interconnected network shaped and sustained by invisible matter. The nodes of this network are galaxy clusters, the most massive gravitationally bound objects in existence. A single cluster can contain hundreds or thousands of galaxies, along with vast reservoirs of superheated gas and enormous quantities of dark matter. These clusters act as anchors, pulling matter along filaments toward their centers. When galaxies fall into clusters, they experience dramatic changes. The dense environment strips away gas, shuts down star formation, and reshapes galactic structure. James Webb has captured these transformations in detail, showing galaxies mid-transition as they're altered by their surroundings. The cosmic web isn't static. It's active, dynamic, and constantly reshaping the cosmos. Yet, for all its influence, dark matter remains one of the greatest mysteries in physics. We still don't know what it's made of. It may consist of unknown particles beyond the standard model. It may involve entirely new physics. Despite generations of experiments, dark matter has never been directly captured in a laboratory. And still, its presence is undeniable. Every galaxy rotation curve, every lensing map, every large-scale structure survey points to the identical conclusion. Remove dark matter from the equations, and the cosmos we observe simply cannot exist. James Webb doesn't solve the dark matter mystery, but it strengthens the case for its central role. By revealing how quickly structure formed in the early cosmos, Webb shows that visible matter alone could never have done the job. Dark matter provided the gravitational head start needed to assemble galaxies just a few 100 million years following the Big Bang. It also explains why the cosmos looks the manner it does today. The vast emptiness of cosmic voids, the dense richness of clusters, and the filamentary bridges connecting them all emerge naturally when dark matter dominates gravity. Yet even this invisible framework operates within a cosmos being pulled apart by dark energy. Dark matter constructs structure. Dark energy stretches space. The cosmos exists in a constant tension between these two unseen forces. On smaller magnitudes, gravity wins. Galaxies form. Clusters develop. On the largest magnitudes, dark energy prevails, driving galaxies apart and pushing territories of space beyond our cosmic horizon. James Webb has shown us that the cosmos isn't merely larger than anticipated. It's more organized, more interconnected, and more dependent on invisible forces than we ever imagined. What we witness, stars, galaxies, nebulae, is only the illuminated surface of a far deeper structure, an unseen architecture holding reality together. And when we step back far enough to consider that structure as a whole, another realization becomes unavoidable. Even this vast interconnected cosmos is only what we can observe from our position in space and duration. Beyond it, the cosmos continues, shaped by the identical invisible forces unfolding beyond any horizon we can ever cross. If you enjoyed this video, don't forget to leave a like and subscribe. It makes a tremendous difference and helps the channel develop.